Hi, this is a continuation of our last lecture, which was on surface areas and volumes. This time we will look at volume. When we talk about the volume of a geometry or of a solid object, or it could be a hollow object, for a solid object we would treat the volume of that object as the space or the measure of the volume of the space that it occupies. But for the case of hollow objects, we could treat the volume of that object as the capacity of that hollow object. When I say capacity, I mean really if that hollow entity or hollow geometry were filled with some kind of fluid, say air or water, just as an example, then the volume of that fluid required would constitute the volume or the capacity of the hollow geometry in question. So with that in mind, let's start by looking at the volume of a cuboid and a cube. So we'll start with the cuboid, obviously, because a cube is simply a special case of a cuboid. So we have our general cuboid here with h height, b breadth, and l length. A cuboid could be looked at as many rectangles with same rectangles with breadth b and length l stacked on top of each other till the height h. So you have numerous rectangles, thin rectangles of this sort stacked up to this height. So therefore we can say that volume of cuboid is equal to the base area into height. So we can write the base area being L into B because it's a rectangular base, and the height being h. We can write the volume as LBH, the volume of a cuboid. And the volume of a cube is pretty easy to find from the volume of a cuboid. For a cube, all that happens is that for a cube, as we discussed earlier, L is equal to B is equal to H, and let's say it's equal to edge length A, then the volume of a cube is equal to A, that is A into A is equal to A cube. So that is the volume of a cube. Next, we will talk about the volume of a right circular cylinder. Recall that we had already discussed as to what constitutes a right circular cylinder. So in this case also we will be talking about only right circular cylinders and not a not a general cylinder as such. So this is a cylinder with a cross section which is circular. The top looks like a circle. This is the, let's just call it the top view, and this is the side view. So the top is a circle of radius r. We could really borrow the concept that we developed here to get the volume of a right circular cylinder. This also can be looked at as a collection of many thin discs of radius r stacked on top of each other up until height h, right? And this radius is r. And so we can again use the general formula that we discussed here. This is true for any geometry which has the same cross section all over its height, which has a uniform cross section all over its height. And so therefore the volume of a right circular cylinder is equal to base area into height, which is equal to the base area here is pi r square, and the height is h. So therefore the volume of a right circular cylinder is pi r square h. Next we will look at the volume of a right circular cone. Now right off the bat I need to tell you that the mathematically rigorous way of finding out the volume of a right circular cone is not in the scope of this course, and so therefore we're best in simply stating the result. So we will not try to prove it because the concepts required to really find out the volume of a cone uh, require many other tools which are not in the scope of this course. So if this were a cone of height h, remember that height and slant height are different concepts. Uh, Refer to the last lecture to get a clarification. And if this were having a base of radius r, we're simply going to state the result here. The volume of right circular cone is equal to 1 by 3 into pi r square h. Even though we did not derive this result, notice something interesting and compare the volume of a right circular cone to the volume of a right circular cylinder. For a cylinder, it was pi r square h, and for a right circular cone, it's 1 by 3 pi r square h. And so, therefore, for a right circular cone of the same base radius and height as that of a right circular cylinder, the volume is 1 by third of the right circular cylinder. That is to say, if a cone and a right circular cylinder have the same height and the same base radius, then the volume of the right circular cone is 1 by third of the volume of the right circular cylinder. That is something interesting that we need to note here. And finally, we will look at the volume of sphere and hemisphere. Again, we do not have the mathematical tools to actually derive the formula from first principles. So we are going to state the volume simply here also. So the volume of a sphere is equal to 4 by 3 pi r cube. 4 by 3 pi r cube. And the volume of a hemisphere is equal to obviously the half of the volume of a sphere. So that is 2 by 3 pi r cube. Again, I repeat, we did not derive this result. We are simply stating the results as such. They can be proved later on with some other mathematical tools that we will develop in higher classes. And so therefore, with that, we come to the end of our discussion of surface areas and volumes. I wish to make some additional comments about the cone. For a cone, there are two heights which were discussed. One is the height h, that is this height, and the height l, that is the slant height. So let's develop a relation between these two so that you can solve questions much more easily. So we know that this is a right circular cone, so this is 90 degrees, and so therefore we know that this is r because this is a base radius, and so this is a this is a right angle triangle, and so Pythagoras theorem is applicable. So we know that L square is equal to h square plus r square. This is a very important result that we need to keep in mind when operating around right circular cones, because this concept is very useful. Say if you have the radius and the slant height and you need to find the volume of a cone, so you can calculate h from this formula first and then put it here simply and calculate the volume, and recall that the curved surface area is pi r l for a cone. And so if you had simply the height and the radius, you can plug it in and get the value of L to calculate the curved surface area. So this is a very important relation that comes into play when we talk about right circular cones. Also, some additional comments when we are talking about surface areas is that the geometry of the object in question is very important. Say for example, you had say you have a box of this sort, right? And it's an open box. So when we talk about the surface area, let's say we want to find out the material required to make this box. We earlier said that the surface area of a cuboid, let's consider that this box is a cuboid, is equal to 2 into LB plus BH plus HL, right? But this formula need not hold for the case of this box, because recall that an open box does not have a lid, and so therefore 1 LB is actually not required, because this formula is for the case of a complete box, complete hollow box, or a complete box. So therefore, for this box without lid, the surface area actually equals to 2HB plus 2HL plus LB, right? There is HB, HB, HL, HL and LB. This LB is not there, and so therefore we cannot use this formula. So and similarly in the case of a right circular cylinder, say if we have a hollow cylinder, completely hollow, something like a tube, right, or a pipe. If we were to find out the surface area of this cylinder, we wouldn't really use this formula, which is 2 pi r h plus r. This is the total surface area given, but the fact that these the two top and bottom portions are missing are not constituted in this formula, but because this is a pipe with no top and bottom, the only thing there is the curved surface area, and so therefore the true surface area of this pipe or tube would actually be 2 pi r h, right? And similarly for the right circular cone, sometimes the base might be missing. Say for an ice cream cone, the base is really not there. So when solving questions regarding surface areas and volumes, one needs to keep their eyes and ears open to really look at the question and decide what all surfaces are there and what are not there. For example, in the case of hemisphere also, a hemisphere, say you have a hemispherical bowl and you find out the area, surface area, then you won't take into account the area of the base, because this is a bowl and the top is open. So with that, we end this lecture. For now, this is all. Thank you.